Hello, everybody. This is Dr. Keto. I'm just here to. Okay, so what we're going to do real quick is go over that last part of the slides that I wasn't able to get to on Thursday. I realize that it is Monday and you have a class tomorrow, so if you don't get to see this by class tomorrow, which hopefully you will, I will make a. I'll make an announcement after I post this to show that it's there. But for now, I'm just going to go ahead and get into it. Okay, so for chemical equations, this is what we are going to be talking about today. So a chemical equation shows you exactly what's going to be going on in a chemical reaction. If you take two different reactants, so that's going to be these right here. Your reactants are going to be on your left hand side, your reactants, and then your products are going to be on the right hand side. These are going to be your products, and if you get them confused, think about the reaction going to you're producing something, right? You're reacting two things together in order to produce something. And the arrow is going to be acting kind of like an equation symbol, or an equal symbol in an equation. So very similar. And so reactants are always going to be written on the left-hand side of the reaction equation, and products are always going to be written on the right. That is always going to be true. Okay? So the key to being able to understand these equations is how they are balanced. And so what's important here is that the numbers of atoms of each element are going to be equal on both sides of the arrow. And so if we look back to this equation, we can see that over here we have two NAs, and over here we have two CLs. And I'll get to what these numbers mean in just a moment. But over on this side, we are also going to have two NAs and two CLs. So this would be considered a balanced reaction. So to balance the equation, it's necessary to select coefficients that make the numbers of atoms of the element equal on both sides. And so that's where you start to get the large 2's and the small 2's and all the large and small numbers. We need to make sure that each of the elements of one substance or another is going to be balanced equally, and so that's very important. And we can verify the work that we do by counting the number of atoms and elements on each side once we're done and everything has been balanced. Okay, so let's give this one an example. So on the next page, we're going to break down exactly how to do it, but yeah, let's continue. So these are the steps that are involved. We want there to be a balanced amount of iron on both sides, amount of sulfur on both sides, amount of oxygen on both sides, nitrogen and hydrogen. And that's really it, because hydrogen and oxygen are going to be accounted for already. And so the first step that would be done to do this is by doing this. So we have a large 1 out here. Now, normally in balanced reactions, if there is only one of a species, one of one reactant, then we do not put a 1. But the 1 is written there so that you can see that there is one Fe, and then over here, one Fe2, and then two Fe's over here. And so remember that this small number, the subscript number, multiplies whatever is to the left of by that number. So Fe2 means that there are two Fe's. So there's two Fe's. And the 1 over here is going to multiply whatever the subscript number is that it is closest to by whatever that subscript is. So 1 Fe to 2 is going to say 1 times 2 Fe's. And so if we look over on this side, we can see just like on the left-hand side, what I was saying before is when there is when there is just one of something, we don't usually write the number. But if you wanted to, just for this example, you would write a 1 down there so that you would be able to see that there is 1 FE, and we're multiplying that by 2. And we're going to do the exact same thing we did before. So that's 2 times 1 FE. So that's 2 times 1 Fe. It's going to be equal to 2 Fe elements. So 2 irons. And so let's continue. We have next up 1 Fe. We've balanced the Fe's, so we'll balance the S atoms next. And so over here, we have this species that is in parentheses right here. So that means if you have a subscript 3 that is outside of the parentheses, everything in here is going to be multiplied by that subscript. So that means that there are, if we're counting the number of sulfurs on this side, there are 3 sulfurs. And so we need to compensate for that on the other side and find where the sulfur is. So sulfur only appears right here. And so there is a 1 in front of the sulfur, even though it's not shown. And we'll multiply that by 3. And so we added this. Note here that there's no 3 to begin with. We add in the 3 right there so that we can multiply everything by 3. And so you get 3 times 1s, which gives you 3 which gives you 3 s's total. So s is 3 over here, s is 3 over here. Great. Now the sulfurs are balanced. Okay. Now I'll show you another trick in just a second after we get to the oxygen part. But normally, if something is in parentheses, or if there is a if it is a polyatomic ion, like we learned about in class on Thursday, then you're going to multiply that everything in parentheses, and you're going to keep it together. So the reason I say that is because SO4 appears over here, and we haven't gotten into the types of bonds yet, but the bonds between S and O are very strong. They're called covalent bonds, and so they stick together. And so in the product, we again see SO4 again. So that means that SO4 is what has been multiplied. But for now, we're just going to count the sulfurs. So let's continue. Nitrogen, we're doing the exact same thing. There's a 1 here that's not shown, so that's 6 times 1. That gives us an N of 6 by multiplying that. Over here, the subscript is is outside of the parentheses, so we'll multiply everything by 2 in there. So there's going to basically be 2 nitrogens and 8 hydrogens, and we'll multiply that by 3, and so we get, again, 6 nitrogens. Or I'll write it so it's the same format as before. N6. There are 6 nitrogens. And so far we have balanced everything that we need to. We've balanced the nitrogens, the irons, and the sulfurs. We still have not balanced the hydrogens or the oxygens. But let's continue. So to balance the O atoms, we need to count the number of oxygen atoms on the left with the known coefficients. And there's 12 oxygens. And so we know that by doing this. We have 3 times 4 oxygens right there. So that is what? 3 times 4 is 12. 12 oxygens in Fe2SO43. And over here, we have 6 times the 1 that isn't there, so that is going to be 6 oxygens over here. And so that is going to be a total of 18 oxygens. 18 oxygens in the reactant side. On the product side, we need to make sure that we have the same things going on. So we have 3 oxygens over here. And we have, 3 times 4 over there. So 3 times 2 oxygens on this side, which is going to be 6 oxygens. And over here we have 4 times 3 again, which is going to be 12. That gives us a total of 18 oxygens. So the oxygens are balanced now. So we have 18 on the left, and we have 18 on the right. So 18 O. I just wrote the same thing again. Whatever. 18 O. O18, and on this side we have O18. So the oxygens are now balanced. And we were able to do that without having to change any of the other numbers that we already had, which is perfect. And so the balanced equation given is correct here. As long as we are able to make this oxygen into put a 6 here so that we have enough oxygens in order to be able to have the balanced equation. And I'm going to show you this again before, since I have a little extra time now that I am uploading a video rather than showing you in person, which is excellent. So the balanced equation is going to look like this. It just has all of the coefficients. If there is a 1, those get canceled out. And all of the coefficients are there. And then we should also check, just to make sure that we're 100% correct, how many hydrogens we have. So we have 6 times 3, which is 18 hydrogens. 18 hydrogens. We have 6 times 2, which is 12 hydrogens right there. There's no hydrogens over here, so that's fine. We don't need to care about that. And we have an H right there, so that is going to be 3 times 1, which is going to be 3, and we'll multiply that by 2 to get 6 hydrogens. And then we have 2 times 4, which is going to give us 8 hydrogens, times 3. So that is going to be, 16 hydrogens plus... Oh my gosh, this is so embarrassing. 16 hydrogens plus... So 24 hydrogens. 24 hydrogens on this side. 24 plus 6 equals an H count of 30. And we have 18 plus 12, which is an H count of, not 0, 30. Which means that we have balanced the hydrogens as well. Sometimes it just works out like that. Sometimes you will have to do a little bit more work to be able to balance the hydrogens, etc. And so we have this balanced equation. So I'm going to go back. Let's see. Oh, just kidding. This is perfect because I forgot I made this slide. So I'll show you how I do it quickly. It's basically the exact same way. I count the number of irons over here. There's 2 irons, Fe of 2. And so we'll just multiply this by 2 over here to get the same number because there's 1 iron right there. So that means that there is now an Fe of 2. And what you want to do is don't balance O until the end. Make sure it's the last thing you balance because oxygen just always is going to mess things up. I used to remember exactly why that is. I do not remember at the moment. Okay, regardless, let's continue. So we have iron with 2 over there. Now I'm going to treat this entire SO4 as its own species. So it's like if it was just a single element, Fe. And the reason I'm doing that, again, is because it stays together as SO4. And you can see SO4 over here. And the reason I know that is because SO4 is the same on both sides, and there is no other source of S present in this. And there are other sources of oxygen, but there's other sources on the left-hand side of oxygen as well. But there's only one source of sulfur and one product that contains sulfur on the right. So I do know that I can keep SO4 together and I can multiply it. And so I know that there are supposed to be 3 SO4s on the left-hand side, but there's only 1 currently on the right-hand side. So we have an S count of 3 on this side, and I'll make it actually an SO4 count, just to make it easier. SO4 count of 3 on this side, there's an SO4, I'll keep it the same way, SO4 count of 1 on this side. So we have to multiply this entire thing by 3. And so keep in mind, you're never going to change the values that are subscripted. Those are always going to stay the same. You can change the multipliers that are to the left of the values you're looking for. That's totally fine. So once we multiply that SO4 by 3, we get 3 SO4s. Now, that did change a value. You should keep in mind that now we have a different value for n. Because we multiplied everything by 3 on the right-hand side, or we multiplied the NH4 to SO4 by 3, we had to change the number of n. So n is now 3 on this side. Nope, n is not 3, n is 6. N is 6 because we have n times 2, and then we have the 2 times 3. So that is going to be 2 times 3 times 1, which is 6. Over here, we have n by itself, just 1. And so we have to multiply this number as well. And so we will do this, 6. Put a 6 right there. And so now what was n has 1 is now n is 6. Okay, so now that we've done all of the other elements, there's only hydrogen and oxygen left over. And usually, it does say don't balance O until the end, but we're basically at the end. Sometimes, like I said, hydrogen just slides into place, and so we're going to balance the oxygen actually before the hydrogen because the hydrogen is just really along for the ride, and we might not have to balance it at all. And so we'll go with oxygen. And so on the left-hand side, there's currently 1 oxygen that is part of this H2O. And keep in mind, there is also oxygen over here, but we said that this doesn't break up at all. This SO4 doesn't break up at all. And so we know that the source of the oxygen on the right-hand side that is over here, the other product that contains oxygen, all of that oxygen must have come from H2O because the other product that has oxygen in it has already been accounted for with this SO4 business. And so what we'll do is we will say, oh, there's 1 oxygen for this hydrogen, this H2O, and we will then look on the other side and say, well, how many oxygens are on the right-hand side? We have 1, multiply that by 3, and then multiply that by 2. And so that's a total of 6, which means we're going to need 6 oxygens over there. So we'll multiply that by 6. The oxygens are part of the water, so we get 6 waters. And then we're basically done. The last thing we need to do is just make sure that the hydrogens are balanced. Everything else is balanced, so the hydrogen should balance, but we should just make sure. And I did this on the previous slide, so to save time, just go back there, and I will see that there are 30 hydrogens on the left-hand side and 30 on the right. And if you want a breakdown on how I was able to count the hydrogens, please just scroll back a little bit and you will be able to see it there. Okay, so now that we are on this slide, let's go ahead and tackle these balancing reactions. I also want to note that I have re-uploaded these slides because this was incorrect. It was, or sorry, not this. This product was incorrect, so I have re-uploaded the slides so you can give these a shot once this is all uploaded. And but go ahead and I will pause here for a moment so you can try these on your own. You can go ahead and pause the video, and we will continue in a second. Okay, so let's start out with this first one. So you will see that we have LiCl. We have LiCl, NaOH going to LiOH and NaCl. This is called a double replacement reaction, in which we have Li and Na switching spots with each other. And also, you might notice that OH is an example of a polyatomic ion, where you have oxygen bound to hydrogen. It's called a hydroxide group, and sometimes these have parentheses around them. However, since this is just one of its kind, there's only one of its kind in this reactant, NaOH, then you are going to not use parentheses because the parentheses are only there for multiplying these. But to make it clear, I will put parentheses around here, and I'll put a 1 down there so we can see that there is one of those. There's 1 there too. And so we'll begin by counting the number of lithiums. There's 1 lithium on one side, 1 lithium on the other. For chlorines, there's 1 and there's 1. For sodium, there's 1 and there's 1. And for hydroxides, there is 1 and there's 1. We're treating this entire thing right here as its own species because it's going to stay together on the other side. Keep in mind this doesn't always happen, but today it does. Okay, and so when we realize that everything is 1 to 1 to 1 to 1, we can realize that this is already balanced. Everything is already balanced here, so we have no work to do on it. All of the elements have equal numbers on both sides, and so we are good to go. That's 1 to 1 to 1 to 1. And so we can just write balanced. And for the next one, let's move on to this one. So Pb is lead, Br3, that's 3 bromide ions. On the right-hand side, we have lead again and molecular bromine. So that means that this is how it exists in nature. This is a molecule of bromine, Br2. And so we are going to balance these. So we have 1 lead over here, 1 lead over here. Great. Now comes the issue. We have 3 bromines on one side and 2 bromines on the other. And I'm going to show you 2 different ways to solve this issue. And they really are the same thing. It depends on how you'd like to work them out, which method you use. So bromine 2, Br2 on the right-hand side and Br3 on the left-hand side, there's a bit of an issue, right? We don't have enough to be able to satisfy both sides. So what we'll do is we'll multiply it. So we'll put a 2 right here, and now that's an even number. Now we have 6 bromines on the left-hand side, and that's going to be something we can work with on the right-hand side. So we can put a 3 in front of the bromine atoms, and then we get 3 times 2. That's going to be 6 bromines. However, when I multiplied this by 2, that also multiplied the number of lead atoms that I have. So we are going to have to multiply that by 2 as well. And then we can check and see if it's balanced. So we have 2 leads, 6 bromines. 3 times 2 is 6. And we have 6 bromines on the other side. Everything is balanced. So that's one way to do it. The other way to do it is a little bit more complicated, but if your brain works like mine, then it might work better for you. So let's explore it. So the lead is still going to be the same. We'll approach it in the same way. Lead and lead are good. Bromine is 2 and bromine is 3 on opposite sides. And so the way that I like to think about this is, if we're talking physically in real life, this is what bromine looks like. It's bromine bound to another bromine. And so we have bromine 2 on the right-hand side. If we want to make it be 3, we're going to need 1.5 bromines, or 1.5 Br2s. So it's kind of like this. We need Br, but we don't care about the half of it. So we can say that is 3 halves, or 1.5, Let's do 3/2. And so the coefficient that's going to go here is 3/2. 3/2 is going to go next to the bromine. Now keep in mind, like I said earlier, I may have said this, but you cannot have fractions be part of your reaction equation. Fractions are not going to work. So what we do to get rid of a fraction is we multiply by the denominator, and then you get a whole number. And we have to multiply everything by the denominator. But before we do, let's just count. So 3/2 of Br2, that gives us 3 bromines on this side, and there's 3 bromines on this side, and there's 1 lead, and there's 1 lead. Sometimes this works out. Now we have the correct number of atoms, we just have to deal with that. We have to deal with the fraction. And so what we'll do is we'll multiply everything by the denominator in that fraction, and so that'll be 2. 2 times 1 is 2 PbBr3. 2 times 1 PBs. 3/2 times 2 is going to be 3. And this is the stoichiometry, which is a word that stoichiometry means the balance between these atoms. This is the stoichiometry that we're looking for. We have everything is lining up now. We have 2 leads, we have 6 bromines, and we're good. That's it. Okay, so we've balanced this one in 2 different ways. Let's move on to the next one. So oftentimes when you're doing this reaction, this type of reaction right here, you will have a similar issue. Where you need to have 3/2 of something, possibly. This is not the case with this one, but keep an eye out for it. And when I say this type of reaction, specifically what I'm talking about is called a combustion reaction. So a combustion reaction occurs when you have something with carbon and hydrogen in it, in the presence of oxygen. Of course, you have to heat it up, but out of it, you are going to get carbon dioxide and H2O. This is every time going to be true. The only thing that's going to change between combustion reactions is the identity of your hydrocarbon, or the identity of whatever organic molecule you have present there. And so always, if I ask you something like what a combustion reaction is, you would tell me a carbohydrate that reacts with oxygen to make CO2 and H2O. So that's always going to be true. But let's go into balancing. So when we balance this reaction, we'll start with C. We have 1 C over here, 1 C over here. Remember, we want to keep hydrogen and oxygen till the end, preferably oxygen at the end, because oxygen is going to mess us up and make us have to do that 3/2 thing pretty much most of the time. But let's make sure that we have the correct number of hydrogens first. So hydrogen, there's 4 hydrogens on the left-hand side, which means we need to put a 2 over here to give us 4 hydrogens on the right-hand side, which then multiplies the oxygens to be 2 instead of the 1 that it previously was. That's no matter because we have oxygen by itself. When you're doing these really long balancing problems, it is always nice to find an element by itself, because that means that it's going to be easier to work with. You can multiply it without changing anything else. And so the total number of oxygens on the right-hand side is going to be 4. Our O count will be 4. And that's because we have 2 coming from here and 2 times 1 coming from there. And so our overall count for oxygens is 4, so we just need to put a 2 right there, and that gives us our answer. There we go. So now there's 4 oxygens, and we can double check. We have 1 carbon, we have 4 hydrogens, we have 4 oxygens on both sides. Perfect. Okay, let's work on the next one. So this one's a little trickier. Let's go through what it is. So this is a combined reaction where you have it's a single replacement and a decomposition reaction. Decomposition, in that this complex right here is not seen on the other side. This CO3 with a 2- charge is a polyatomic ion, and you don't see CO3 on the other side. You see CO2, but you do not see CO3. And so let's get into why that might be. And so we cannot treat CO3 as an entire like a single molecule anymore, because it decomposes. It's not on both sides. Whereas with hydroxide over here, we were able to do that because hydroxide stays intact on the other side. But it doesn't stay the same for CO3, so that's not the case here. First, let's balance the tungstens. We have 1 and 1. That's excellent. Then we will go to, we're going to try to do the we're going to try to do the oxygens and hydrogens last, as per usual. So let's do the carbons. And we notice that there is 1 carbon here, and there is 1 carbon here, there are 2 carbons to begin with, and there's 1 carbon on this side. There are also 2 carbons here, but if you will take a look at this right here, the other reactant, then you'll notice that we have something similar to the OH debacle that we already dealt with. So C2H3O2, this is the ratio of atoms, and it stays together on the other side. So we know that all of the C2H3O2 that ends up bound to this tungsten is going to come directly from, it's going to come directly from the C2H3O2 that has this H out here. And so you might be wondering, if you have C2H3O2, what is that? Why is this H out here? HC23, whatever, HC2H3O2. Now, you might remember that I said that if there is an H in front of your molecule, there is a good chance that that is going to be an acid, and that is the case here. This is called acetic acid. Acetic acid, which means that acids, in their nature, separate the H away from the rest of them. So that's how we're able to separate this H. It's called the acidic proton, or the acidic hydrogen. Either one is fine. And so we're going to look at that as its own species. But let's continue with where we were before. So we have gotten to carbon CO3 with a 2- charge. And so if all of the carbon that comes from this species came from the acetic acid on the left-hand side, then that means that the remaining carbon is going to come from the CO3. And so that's why we don't see it on the other side, is because it decomposes into something else. It's going to decompose into CO2 and H2O. And so we have CO3 on this side, which gives us 2 carbons. We have carbon on this side, which we're going to need to multiply by 2 in order to get the same number of carbons on both sides. And we're going to do the oxygens last. That's where we'll deal with that. But for now, let's move on. So we know that we can treat this acetate as a polyatomic ion. Also, just as a side note, sometimes it's written like this: CH3COOH. This is the same thing. It's called an acetate ion. I'll draw it over here. You have a CH3, you have a carbon in the middle, and you have an oxygen, and that oxygen is bound to a hydrogen. And so you don't need to know how to draw that. We'll get into that later on. But CH3COOH is another way to write it. Either way is fine. Anyway, so we have this acetate bound to here, to the tungsten on that side, and we're going to need to have 4 of them. So 4 are going to go over in order to balance everything out, right? We need 4 of these C2H3O2s on the right-hand side, so we'll put a 4 right there. Now we can pay attention to the number of hydrogens that are left behind. So the hydrogens are going to, they were multiplied by 4, And so all of the hydrogen that does not come from the acetate ion, that is right here, belongs to this H2O in the products. And so we can put a 2 right there in order to multiply the H2 by 2, and we will get 4 hydrogens on here, 4 hydrogens from there. That's perfect. Then we have 4 over here, we got a 4 over here. Everything is looking pretty good. Now let's see if we need to do anything special with the oxygens. So we have all of the oxygens that are part of the acetate ion are still part of the acetate ion in the right-hand side, so we don't care about those. So the only ones that we're going to be dealing with are going to be oxygens that come from the CO3. So we know that there are 6 of those on this side. And we know that there are going to be 2 times 2 times 2. So that's going to be 4 oxygens there. And 2 times 1 is going to give us 2 oxygens here. So that 4 plus that 2 is going to come together to give us 6. O count of 6. And we have an O count of 6 over here. And we are balanced. That's it. We did everything. So I'll erase all of this just so that we can see everything. We'll go ahead and delete it. We have, I won't delete the stoichiometry though, and we'll go ahead and check it. We have 1 tungsten. We have 2 carbons that don't come from the acetate ion. We have 6 oxygens, and that's 2 plus 4 plus 2 times 2 plus 2 is 6, and so we have 6 oxygens. We have 4 hydrogens from the acetate ion, and 4 hydrogens over here. Perfect. And we have 4 acetate ions that come from multiplying this by that, and we have 4 acetate ions over here. And we are finished. Okay, like, comment, subscribe, or whatever. Bye.